Hello and welcome back to Physics Competition. In today's video we're gonna solve the problem from kömal magazine about the hemispherical shell and charged bead. So let's get started. A hemispherical insulating shell is charged positively and is fixed. The charge distribution on the shell is uniform. At a point on the symmetry axis, which is exactly at distance of the radius measured from the center of the hemisphere O, a small negatively charged bead is released. The speed of the bead is v0 when it reaches the center O. What will the speed of the bead be when it reaches the shell? At first glance, it might seem that the problem should be solved by dividing the hemispherical shell into individual elementary charges and analyzing the interaction of each with the bead. However, this approach would be too complicated. Instead, I suggest a simpler method. Here's the idea. Let's extend the hemispherical shell into a full sphere. Let's call the upper part B and the lower part A. According to Gauss's law, the electric field inside a complete spherical shell is zero. Let's try to prove that electric field inside the sphere is indeed zero. First, let's recall the formulation of Gauss's law. The flux of electrical field through a closed surface is equal to the charge enclosed within that surface, divided by the electric constant. Now, let's draw a closed spherical surface inside of a spherical shell. Due to the symmetry of the sphere, the electric field on the surface will have the same magnitude at all points. That's why I'm drawing vectors of equal length for the electrical field. Let's write down a Gauss's law. The sum of the elementary fluxes for the closed surface, in this case the sphere, is equal to the charge inside the surface divided by the electric constant. On the other hand, the flux can be expressed as the sum of elementary fluxes, each of which is the product of electric field strength and the area of an elementary surface. Since the field is the same at all points, due to symmetry, it can be factored out of the sum. Thus, the flux is equal to the product of electric field strength and the total area of the sphere. The area of the sphere is not zero, but the flux through it's zero because there are no charges inside the sphere. This means that the electric field strength on the surface of the sphere is zero. Using the same logic, we can draw many smaller spheres inside the shell and confirm that the electric field is zero at all points on the spheres as well. Since we can draw an infinite number of such spheres, this proves that the electric field inside the spherical shell is zero at all points. Now let's recall what potential is. We know that the electrical field strength is equal to the negative gradient of the potential. Since the electric field inside the sphere is zero, the potential difference between any points inside the sphere is also zero. This means that the potential is the same at all points inside the sphere and equals some constant. Typically, this constant is chosen to be zero, so the potential at every point inside the sphere is also zero. Let's recall what our spherical shell looks like and draw it again. Let's choose an arbitrary point inside the shell. The potential phi at this point can be obtained as the sum of potential created by each of the hemispherical shell, phi A and phi B, due to the principle of superposition. However, since we've agreed to set the potential to zero, it follows that the potential created by hemispherical shell A is equal to the negative of the potential created by hemispherical shell B at the same point. What we can do next? Let's introduce a coordinate system. We'll draw an axis along the axis of symmetry and label it as the x-axis. The origin coincides with the center of the sphere. The topmost point has a coordinate of plus r and the bottommost point has a coordinate of minus r. Now we can write that the potential created by hemispherical shell A at this point with coordinate plus r must be equal to the negative of the potential created by hemispherical shell B at the same point. Next, using symmetry consideration, let's consider a point near the bottom of the hemispherical shell A. Its potential is denoted as phi A minus r, Now let's consider the symmetric point for hemispherical shell B. At this point, the potential must be the same, as it's simply a reflection of one hemispherical shell across the horizontal axis. Thus, the potential of hemispherical shell A at point -r must be equal to the potential of hemispherical shell B at point +r. Applying these two equations, we conclude that potential created by hemispherical shell A at point +r is equal to the negative of potential created by the same shell at point -r. That is, at a distance equal to the radius from the center of this hemispherical shell. Now recall the potential inside the sphere must be 0 at all points. However, due to symmetry, at the center of a spherical shell, the potentials of both hemispherical shells are equal, and their sum is 0. This means that the potential themselves at the center of spheres are also 0. Let's make another diagram to plot this potential. For hemispherical shell A, at the center the potential is 0. At a top point, at the distance equal to the radius from the center, the potential is minus phi0. At the bottom point, the potential is plus phi0. Now let's consider the work energy theorem. The change in kinetic energy is equal to the work done by the electric field. The work done by the electric field on a point charge is equal to the product of the charge and the potential difference between the points. Let's write this for 3 states. State 1, the bead begins to move. State 2, the bead passes through the center of the hemispherical shell. State 3, the bead collides with the hemispherical shell. The change in kinetic energy between states 1 and 2 is equal to the product of the bead charge and the potential difference between these points. Since the potential at the center is 0, the change in kinetic energy on this segment is Q times phi0. The increase in kinetic energy on this segment is equal to the kinetic energy when passing through the center, since the initial kinetic energy is 0. Similarly, for the transition from state 1 to state 3, in state 3 the kinetic energy will be different and the initial kinetic energy is again 0. The potential at point 3 is plus phi0 and at point 1 it's minus phi0. We notice that the work done by the electric field on segment 1,3 is twice the work done on segment 1,2. Therefore, the change in kinetic energy on segment 1,3 is twice that on segment 1,2. This means that the kinetic energy on point 3 is twice the kinetic energy at point 2. From this, we find the expression for the bead's velocity at the moment of collision with hemispherical shell. This velocity must be square root of 2 times velocity of the moment of passing through the center of the shell. And that's it. This is the solution. This is the answer to the problem. If you enjoy solving physics problem or are preparing for competition, don't forget to like, subscribe and hit the bell icon for more content like this. Join my Telegram channel for additional physics resources and problem solving tips. See you next time.